P is a vector of magnitude 34 centimeters. Q is a vector of magnitude 13 centimeters. If tan of A equals 4/3 and tan of B equals 5/12, write vectors P and Q in terms of I and J. We saw in the previous video that any vector R can be written as R cos theta I plus R sin theta j, where R without an arrow is the magnitude or length of vector R, and theta is the angle measured from the positive x-axis anti-clockwise to the vector. Let's look at vector P. Its magnitude, denoted P without an arrow, is 34 centimeters. We can see that for vector P, theta, the angle measured anti-clockwise from the x-axis to the vector, is an acute angle. It's an angle between 0 and 90 degrees. It's referred to as angle A here, but I'm just going to call it theta now, just to be consistent with the general notation for a vector. So instead of R, we can write P. So vector P is P cos theta I plus P sin theta j. So we have P, that's 34. We just need to find cos theta and sin theta. Well, we could just get the inverse tan of theta, or sorry, the inverse tan of 4/3 to find theta, and then just get the cos of that angle and the sine of that angle, and then we can get P in IJ form. Of course, another way that we can get cos of theta and sine of theta is to consider a right angle triangle where we have angle theta. Make the side opposite theta 4, make the side adjacent 3, so that the tan of theta is 4/3. That's what we want. And from this we can work out the sine and cos of theta without getting theta directly. By Pythagoras' theorem, the hypotenuse of this triangle is 5. 4 squared plus 3 squared is 5 squared. So now we can write down the sine and cos. Cos theta is 3/5, sine theta is 4/5. We multiply by 34 to get vector P. For vector Q, the magnitude, that is Q without an arrow, is 13, so that's the length of this vector here. And theta, tan of theta is 5/12. So theta is this angle here. It's called B for vector Q, but in general we call it theta. So this is the general form of a vector. So as before, we follow the general form of a vector in the IJ plane. So we now have this for vector Q. We don't know what theta is, but we know that the tan of theta is 5/12. So from that we can work out the cos of theta and the sine of theta. So just like before, we construct a right angle triangle, make the side opposite theta 5, make the adjacent 12, get the hypotenuse from Pythagoras. The hypotenuse is 13 here. You can check that 13 squared is equal to 5 squared plus 12 squared. So cos theta is 12/13, sine theta is 5/13. Plugging those in, we get vector Q equals 12i plus 5j. Next, we want to show that vector P plus Q makes an angle of 45 degrees with the I-axis. When they say 45 degrees with the I-axis, it means 45 degrees with the positive I-axis, presumably. First, we get vector P plus Q. Well, that's straightforward. We add these two vectors. We just add the I components. 20.4 plus 12 is 32.4. 27.2 plus 5 is 32.2. Here is a picture of vector P plus Q. We can see that it is indeed in this first quadrant. So we're interested in the angle it makes with the positive x-axis, or the I-axis. So here's our angle theta. In this right angle triangle, we see that tan of theta is 32.2 divided by 32.4. This is a number that's very close to 1 actually. If this number was exactly 1, then theta would be exactly 45 degrees. But it's not. But we're going to get an angle that's very close to 45 degrees. You know, if tan of theta is 1, then this side of the right angle triangle would equal this side. So we would have an isosceles right angle triangle, which means that these two, if the two sides are the same, then these two angles have to be the same. So both of these angles would be 45 degrees. In particular, theta would be 45 degrees. To 2 decimal places, I get 44.82. So if we round this to the nearest degree, we could write down 45 degrees. If minus 7i plus j and p times I plus j have equal magnitude, where p is some positive number, find the value of p. Now here is the magnitude of minus 7i plus j. We square the two components, add them, and get the square root. Now let's get the magnitude of the second vector. P is just a number multiplied by this vector. The magnitude of this product is actually the product of the magnitudes. So we have the magnitude of P. That means that we just take the absolute value of this number P. Well, P is positive, so the absolute value of P is just P. If P was a negative number, well, we'd have to make it positive by putting a minus sign in front of it. Here, the magnitude of P is just P. The magnitude of 1i plus 1j is the square root of 1 squared plus 1 squared, or the square root of 2. Now another way we could have thought of this is simply to multiply P into the vector, because P is just a scalar, so we'd have Pi plus Pj for our vector. So we want to get the magnitude of this vector. So the I component is P, we'd square it. The j component is P, we square it. We sum the squares of the components, so we get root 2p squared. We take the square root sign over each factor in here, so we've root 2 times root p squared. Well, root p squared is just p, same as before. These two vectors have the same magnitude, so root 2p equals root 50. So root 50 divided by root 2 can be written as root 50 over 2. 50 divided by 2 is 25. Root 25 is 5. Now that we've established that p is equal to 5, we know that the second vector, p into I plus j, must be 5i plus 5j. Now we are interested in the smaller angle between these two vectors. So I have a sketch of the two vectors. The smaller angle between them is this angle here. The larger angle would be this one here. I will start by getting angles A and B. A would correspond to theta for this vector here, because it's measured anti-clockwise from the positive x-axis. We see that the sides of this right angle triangle are 5 and 5. So the tan of A is 1, so A is 45 degrees. If we look at angle B, the side opposite angle B has length 1. The side adjacent to angle B has length 7. So I'm only dealing with lengths here, not the actual coordinates at this point. So the lengths are positive. So we can see that tan of B is 1 over 7. So to find the angle C, the smaller angle between the two vectors, we take 180 and subtract angles A and B from it. A is a vector of magnitude 10 units as shown. B is a vector pointing in the negative j direction. Find the value of k if A plus B equals k times I, given that tan of A equals 3/4. Vector A is actually fully specified. We have its magnitude, which is 10, and we also have this angle here called capital A, because we know that tan of A is 3/4. B, however, is not fully specified. We know its direction, it's pointing in the negative j direction, but we don't know its magnitude. We know that any vector A can be written like this, where A without the arrow is the magnitude of A. Theta is the angle measured anti-clockwise from the positive x-axis. Theta is just capital A in this case. We can find cos theta and sin theta by considering this right angle triangle. We're given that the tan of A, or tan of theta, is 3/4, so A is just theta, remember. So we can draw a right angle triangle. Take the side opposite theta to be 3 and the adjacent to be 4, so that the tan of theta is 3 over 4. From Pythagoras, the hypotenuse here will be 5. The root of 3 squared plus 4 squared is 5. So now we can get cos of theta and sine of theta. So vector A is the magnitude of A, which is 10, times the cos of theta, which is 4/5, and the sine of theta is 3/5. Here we have 10 divided by 5 is 2, so 2 4s are 8, and we have 2 3s are 6. So vector A is fully specified. What about vector B? How are we going to write vector B? Well, since we know it's pointing in the negative j direction, we know that its I component is 0, so we could write 0i. But normally we don't bother writing that. We just leave it out. The j component is going to be minus b actually, where b is the magnitude of the vector. So b is the length of this vector. B would be a positive quantity. The length is always positive. And we take the unit vector pointing in the negative j direction. That unit vector is a vector of length 1, of course. And we just scale it up by this factor of b. So the unit vector is minus j. So b times minus j, or minus bj. Of course, we could get vector b by referring to the general form of any vector, as we covered in detail in a previous video, just like we did for vector a as well here. We don't know the magnitude b, but we know what theta is. Theta is measured anti-clockwise from the positive x-axis. So theta here is going to be 270 degrees. So what we get is b times the cos of 270 degrees times I, plus b times the sine of 270 degrees times j. The cos of 270 is actually 0, so we will get 0i. That's what we want because b has no component. The sine of 270 is actually minus 1, and so we plus b by minus 1j, or minus bj. So as before, we get minus bj. But of course we don't need to do all that. We can just, for any vector lying on the j or I axis, it's quite easy to get its ij form. I is 0. We take the magnitude to be b. That's b without an arrow. And it's a negative vector, so we need a minus sign. It's in the j direction. Now, we see that the sum of the vectors a plus b has got to equal k times I. Well, let's get a plus b. How do we do that? Well, we add the I components of the two vectors. Well, the I component of this vector is 8i, and we add it onto the I component of this vector. Well, there is none. So we're finished with the I component. Now look at the j components. We take the j components and add them together. So we have 6j minus bj. Of course, we can factorize out the j and write this as 6 minus b times j. So that's just addition of vectors. Add the I components, add the j components. Now we want this to equal k times I. So k times I is actually a vector pointing along the I-axis. It has no j component. You could put in a 0j here if you like, to emphasize that. So we want this vector to equal ki. The only way two vectors can equal each other is if corresponding components are equal to each other. So the I components must equal each other. So in other words, 8 must equal k. So we found k. K equals 8. Now the j components must equal each other as well. The j component here is 6 minus b. And on the right hand side there's no j component, so we could write 0j. So that 6 minus b must equal 0. From that we can find b. b must equal 6. As a matter of fact, we're only asked to find k. Let's see what this means geometrically. Since we also found b, we found that b is 6. We know that the magnitude of this vector here is 6. So now we know that vector b must equal minus 6j. So we have vector b fully specified. So this point here has coordinates minus 6. Anyway, if we add a and b together, we will get a vector that's lying along the I-axis. If we do this geometrically, we could sum the vectors by the parallelogram law. We just construct a parallelogram and draw in this diagonal. And this diagonal is the sum of the two vectors. This diagonal is k times I, where k is 8. So this vector is 8i. So this point here is 8 on the x-axis. So the sum of a and b has no j component.